Hi, I'm Dr. Laird, here to answer your stupid astronomy questions. The questions that I have submitted to me are not necessarily stupid, but they are remarkably uninformed. But before we begin, let me just point out the icon behind me. I have that on my business card, and that is the planet Saturn. But unlike pictures of Saturn you may normally have seen, this one was taken from behind. So that Saturn taken with the sun in that direction. And there's a glint of sunlight right there from where it's making its way through the atmosphere. And right over here is planet Earth. And when this picture was taken, everybody on planet Earth who was signed up for the email was informed to wave when the picture was taken. So if you are among those people who are waving, there's you right there, right then. Okay, so we begin. So this question and the next four were submitted by Neil Tanner, who was unable to attend our 60th reunion. And his question is, first question, with our bodies being bombarded by millions of neutrinos per second, why don't we feel them? If it is a matter of being accustomed to them, is there some place where we could go to be shielded from them? And the answer to that is no, there is no place that you could go to be shielded from them. They are, in fact, everywhere. There is approximately 300 of them per cubic centimeter right now. And some of those I had it right for you. And the only way you could stop them from penetrating your body would be to shield yourself with a light year of lead. And that would give you a 50-50 chance of, well, that would reduce the bombardment by 50%. So really nothing. When they build neutrino detectors, they build them underground because the neutrinos penetrate the Earth. So there's nothing that can be done. On the other hand, neutrinos, because they do not interact with matter very strongly, they also will not interact with you very strongly. So the chances of you being hit by a bad one and converting some of your gene into something that's not so nice is kind of slim. On the other hand, that's what happens. Cosmic rays are more likely to do it to you, but you have to be above ground to have that happen. Neutrinos can, mess with your genetic material anywhere it wants to. So no hiding from neutrinos. Question number two. The penumbra appears at the edges of the shadow that occurs as day changes to night and night to day. Scientific definitions of the penumbra assume a point source of light, which is not true. So the question's wrong so far. But the sun is not a point source of light. My question is, at sunrise, how long before this defined start of penumbra does the first diffused light hit the Earth? And see, again, that's not a good question. The sun is half a degree in diameter. And when the sun sets, it's going to set within a minute and it's just going to fall apart. It's going to just drop below the horizon. Twilight is that period of time where the sun has dropped below the horizon 6 degrees. That's twilight. And then there is what they call nautical or navigational twilight, where the sun drops another 6 degrees below the horizon. And you can see the stars at that point. But you have to wait until astronomical twilight, another 6 degrees, a total of 18 degrees, before the stars are fully visible and there's no more scattered light in the sky. So this business about penumbra misses the point that the light is being scattered by the atmosphere. And it's not about the angular size of the sun, which does have something to do with it, because that little bit of sun as it drops below the horizon does a little something, but you're really more concerned about the 18 degrees of drop, not the 1 degree or half a degree that it drops while it's, setting. So thank you very much for the question. Question 3, can you think of an astronomical practical joke our class could play on someone in the engineering school, administration, or faculty that would endear us to them and create a lasting legacy for our class? So of course I can't, but because we have ChatGPT, so I asked ChatGPT that exact question. And it came up with a really dumb idea. And I'll tell you the dumb idea. And its dumb idea was, say that we can see this special star from our campus, and so it's because we're on campus that you can see this special thing. And you can make up some stuff about the special thing. The point is, if you can see it from our campus, you can see it from anywhere on Earth. So I pointed that out to ChatGPT and apologized for its stupidity. And I came up with a better idea. And that one is, have AI inspect the sky for some symbol that is unique to Columbia University engineering, perhaps their shield. Have the AI look through the sky to find that symbol, and then create an app on your phone that literally, when you point it at the sky, it picks out those stars that are unique to Columbia University and says, this is put there by Columbia, not put there by, something commemorating Columbia University. It's unique, it's special, and it's like just as stupid as finding meaning in the Bible by doing numerology in the Bible. This way you're doing numerology on the stars. And if you can convince the unsuspecting public of this using an app on your phone, maybe you can get away with something. That's better. I don't think it's great, but it's at least ChatGPT's second try. I'm not going to try again. Thanks for the question. So when was it proven that the moon was not made of blue cheese? Well, first of all, the moon has never been accused of being made of blue cheese. It's usually green cheese. So with that in mind, same question, different color. I think the moon has never been proven to not be made of green cheese. The only way you can do that is by inspecting all of the moon. There might be places on the moon that might be made of green cheese. And the only way you can actually determine that is to completely survey the surface of the moon. So your hypothesis that the moon is made of green cheese is impossible to disprove. And also, it's also pretty impossible generally to disprove a negative. So basically, you're trying hard to do something that's impossible to prove. You can't prove that there isn't a teapot in orbit around the sun, which is too small to be observed by telescopes. That's called the Russell's teapot. And it's just as hard to disprove as disproving that the moon is not made of green cheese. Thank you very much for that stupid question. Question number 5 from Connie, and it is, should we attempt to colonize any planet or moon? Won't we ruin it? And what do you mean by ruin it? That's the problem with that question, because, I mean, we're ruining our planet for sure, but in 100 million years, nobody will care. So it'll sort of put itself all back together again. And the only thing we will have ruined is we will have used up all the coal and gasoline and petroleum. So if you consider that ruining a planet, yeah. But aside from, and ruin it for the next species that comes. That'll be great. They won't be able to develop atomic weapons without the aid of fuel and petroleum. So, maybe we're preserving it for future generations. As far as the moon, we might rake the moon for helium-3, which is the best thing you can use when you're making nuclear fusion. You need some of that. But then all we'll do is just rake the moon. It won't look the same, but it'll look different. So future generations won't have our pretty moon to look at. Actually, if you rake the moon with for helium-3, it's just the top layer you're looking for. So it'll look the same. So I don't even think we could ruin it. We could ruin it if we put a big advertising sign, like a giant park, advertising Coca-Cola or something. That could ruin it. Otherwise, I think not a chance. Not a chance that we might ruin it. And so we can go there, no problem. Thanks. Well, this one seems to come from Chervin. I hope it does. Uh, uh, and he writes, uh, it may not be Chervin, but assuming it is, if there are 100 billion stars in our galaxy, and I'm in favor of 400 billion, let's but not quibble, why is the night sky so devoid of light? And that's interesting. There is this is not the question that was often asked, which is why, if there's an infinite number of stars in the universe, why isn't the sky very bright? And this is not that question, because he's not talking about the universe, he's talking about a galaxy. It's a different question. So this one's somewhat unique. But the answer is, the reason is because the stars are far away. So I asked ChatGPT, to confirm my back of the head envelope calculations, and it did the math. I said, assume they're the same brightness as the sun, but their intensity is diminished only by distance, and not by cosmic dust, and do not take into account the fact that most stars in the galaxy, the majority by a factor of like 10, are dwarf stars, much dimmer than our star. Mars is a dwarf star, but it's a G2 dwarf, not it's a yellow dwarf, not a red dwarf. Anyway, assuming G2 stars like our star, the diminution of the light due to the R squared law would make that light very dim from every star that's coming our way. So in the end, that alone, ChatGPT calculated it, would be unlike dimmer than our sun by a factor of like 1,000,000 times. I forget the number. It could have been 100 million times. But it's just because of the inverse square law and nothing else. You'd have to really pile a lot more stars in the sky before you could get the Milky Way looking bright enough to light up the daytime. So if that was you, Chervin, thank you very much. I really appreciate you weighing in on this. This one is question number 7. No, not attributed to anyone. And it is, what is the probability that somewhere in the universe, human-like species, meaning, I assume, intelligent, has evolved aside from us here on Earth? And you want to know the probability. And so does everybody else. So why would you think that I could possibly answer a question like that based upon one data point, which is me or you? That doesn't make 2 data points. It's still 1. We have one example of life. We are going to Mars to find if we can find a second data point. I don't think it's a good place to go, but it's close. So let's go there first. Enceladus, which is a moon of Saturn, is a great place to go because the chances of life having originated there and having been spread to Earth or vice versa is virtually nil. But the chances of life being spread from Mars to Earth or vice versa is very high, like given. So that if we find any DNA on Mars, it won't mean a thing, unfortunately. So we have to go elsewhere to get that second data point. The second data point would tell us that life is probable, which we don't even know, but we suppose. So supposing that life is probable, then you need a whole series of really amazing things, which made us. And I think more of the amazing things are in the realm of biology, which I took in high school, but not in college, so I can't speak to that. Although if you check my YouTube videos, you will find I'm do talking about it in class as to answering this exact question as to how you could explain how amazingly rare we are. So, but there's still no numbers. So knock yourself out, make it up as you go along. Thanks. So question number 8, which is written by Connie. What is a good definition of space? Not, as Connie says, the place where you park your car. Okay, that's fair. Space is really hard to define because, of course, well, it's. I'm not going to be able to do that, but I would point out that when you talk about space, you are missing one of the dimensions in the 3D, version of space and time and all that. You need space-time, which is the fourth dimension. So what is a good definition of space-time would be the better question. And then it's the thing that mass can bend. I don't know. It's empty, except if you're talking about quantum mechanics. Let's ignore that. In quantum mechanics, you can imagine space being having little things popping in and out of existence in quantum times and quantum space. But that's still empty space because it's below the Planck limit. Space itself is supposed to be empty. Oh, again, there's another problem because dark energy seems to inhabit space. So again, is that part of space? I don't know. Dark energy is a story, and who knows if it's part of space. It's something we have to explain, but it's maybe or maybe not space. It's looking like it's supposed to be space, but anyway, space is empty. It's made of 4 dimensions, and that's it. That's all I got. Thanks. And number 9, traveling at 50,000 miles per hour, a vessel would take 53,000 years to reach the closest star to us, Alpha Centauri, located 40 light years away. Owing to the immensity of stellar distances, the likelihood that humans will ever visit another star system is very small, and vice versa for aliens reaching us. Am I right? Sure, you're right. The problem with going here and going there is that is this nasty little bugger called the rocket equation, which essentially says you have to take your fuel with you on your way, and you lose it on the way. So essentially, you can launch a rocket with a small payload, but you need a Saturn V to put something small enough, powerful enough to get to the moon and back. But mostly it's fuel. So if you're building something to go to the nearest star and you want to get there in any kind of reasonable time, that thing has to be very big. And the thing that you're sending has to be very small, like this small. But you want to send 2 humans, let's say, to the nearest star. Let's put them in suspended animation, and let's get them there as quickly as possible. Let's do that using the most efficient way that you can make anything go, and that is, let's smash matter and antimatter together, producing pure energy. Let's imagine that pure energy can be turned into kinetic energy to power the spaceship. And so, given that, you can get, with just about 50 pounds of matter and 50 kilograms, I looked it up, 50 kilograms of antimatter and matter, you can smash those things together, and you can get 10% of the speed of light, and you can get there in less than 100 years. So you can get 2 passengers, 2 Alpha Centauri. We're not slowing them down, just sending them whizzing past, but nevertheless, in less than a human lifetime, at 10% the speed of light, with just matter and antimatter. What could go wrong? Just about everything. because matter when antimatter, when they sort of combine, they do a nasty thing. They create radiation of all sorts, and that radiation is terribly lethal. So you have to shield this rocket from the antimatter and the matter. So you just made the rocket bigger, which means you have to make the antimatter bigger. So you're pretty much building an enormous rocket to send two people in suspended animation there. And assuming you can get the shielding right and the fuel right, uh, you could get there, wake them up and say hi. Uh, so it's not completely impossible, but there's so many ways that it is impossible that the best way to do it is don't send people. Send robots, which don't need any kind of life support. Send uh, uh, embryos, which require extensive life support if you want to raise them to be thinking human beings. Uh, or you can send a generation ship. Generation ship is science fiction. You send them for thousands of years to get someplace. But these generation ships, when you concoct the mass that you've got to send and the amount of fuel and how slowly they're going to go, uh, they're going to take tens of thousands of years to get there by any scenario. So, so the best thing to do if you want to populate the galaxy is this thing called Van Neumann machines. And what you do is you send a Van Neumann machine, which is only a machine that can do one thing, and that's reproduce itself. Okay, that's its job. It lands on a planet, it makes another one of itself. So however that takes to do that, that's how big the machine is. Then when the machine has two of it, you can make four of it. When it's made four, it can do, math. So eventually it's really big, and now it can take on another task, which is to build a civilization of machines that can build Van Neumann machines that can be launched into outer space. And if you imagine that you can build a Van Neumann machine on a planet that it lands on in 5,000 years, and then, in other words, build the infrastructure that you can then use to send up another Van Neumann machine in another direction, you can populate the galaxy in 1,000,000 years. So where's everybody? It's a good question. Anyway, that's it for me right now. Thanks a lot. Bye. I'll be on to the next question. Number 10, saying that the universe is expanding is misleading. It's actually not, because it gives the impression that the space in which we live, whatever space is expanding. That's right, because it's the impression that we're intending to give. What is actually happening is that on a large scale, the density of matter is decreasing as large clusters of galaxies are receding from each other. Am I correct? Yes and no, but mostly no. And the thing we call space is not expanding. No, it is. So space, so this little problem we have with space and time and all that stuff. Universe began 13.8 billion years ago. That's a fact. The universe, however, should be no bigger than 13.8 billion light years, but it's not. It's bigger than that. In fact, the size of the observable universe, observable means with any instrument we have now or could invent in the future, is 46 billion light years in that direction, and another in that direction. And so space has expanded faster than the speed of light, which is amazing, but it did. And it took, along with it, the things that were in it, those galaxies, for example. So the galaxies can do their own thing and move around and interchange with each other and expand or contract. They do whatever they want to do, independent of the expansion of space. That's locally, but as soon as you go further out, it's the expansion of space that's doing it. The universe, when it was little, was smaller, and space expanded and took the matter with it, which is really amazing. One of the amazing things in the story of the Big Bang, it is one of the most ridiculous stories, nevertheless believed by scientists who know better than I. Uh, Very early in the beginning of the universe, and when I say early, I mean fractions of a second that look ridiculous, like 10 to the 20 to the minus 26th second, really small fractions of a second. The universe expanded in that small period of time 10 to the 30th times in that fraction of a second. And that's, of course, space. And if it didn't, we wouldn't be here. Because that's and then the Big Bang started. So the Big Bang is after that enormous expansion. Then the universe started to expand, and matter was created out of the energy, and eventually we got to be here. But it's space that's expanding. And so the question and the assumptions is all wrong. Thanks. But then Connie asked again, is the universe pulsating? Or, i.e., on a large scale, is the density of matter alternately decreasing and then increasing over enormous stretches of time? And that's a good question, to which the answer is we don't know, but best guess, no. So far, that's called the oscillating universe theory, and you can't say no to it. But uh, but but let's go sort of to what's the story that we have right now, which is that a Nobel Prize ago, there was a group of scientists who decided to look at the universe expansion rate, see how much it's slowing down, because it makes sense. Gravity pulls it back. So even if it was expanding over time, and we know that it is expanding, the question is it slowing down? So let's see how much it's slowing down. And then we could see, it's going to bounce back and it's going to contract again, and then it's going to bounce back again. That would be how your question would end up, like an oscillating universe. So they went looking for a universe that was slowing down. And then what they found instead was a universe that was speeding up, which is insane. They got really upset. They got very, very happy. They got a Nobel Prize. Turns out it's true. It's really true. It's surprisingly true. There's so much evidence that it's true. The universe is expanding at an increasingly accelerating rate. That's the news as it stands right now. There are some people who are saying, maybe hold your horses, maybe not. But that's today's news, and I wouldn't trust it until tomorrow. So the universe is expanding at an accelerating rate and probably not oscillating. But we don't know. Thank you, Connie. Now, Bill Lepatkin asked question number 12. Here's another question for Laird. Everything I can think of relating to why we were able to evolve on Earth relate to our local environment: stable solar orbit at the right distance, moon to stabilize the Earth's axis, and characteristics of the Earth itself, such as tectonics, which you didn't mention. Yeah, that's what you meant. Are there any other factors related to our place in the cosmos, be it our place in the Milky Way or relationship to other galaxies, that would relate to the ability of Earth to evolve complex life? And the answer to that is yes. You know that our solar system has a habitable zone, and it includes Venus, which didn't do too well, habitability-wise, and the Earth, which got the gold star, and Mars, which is yet to be determined whether it ever, pulled off a life birthing event. That's the habitable zone of the solar system. But it turns out the galaxy has one too. So let's investigate. If you go really close to the center of the galaxy, where there's this big black hole, and not that very big, it's small compared to many, 4 million solar masses, but not 4 billion like Andromeda. So there's lots of stuff. There's lots of stars there, right? And they are by their very nature would have something to say about our own sun. Were we born there? Uh, and the things that they might have to say might be, uh, we will explode near you rather than far away from you. We could collide with you if you're very close to the center of the galaxy, or we could mess with your orbit around the galaxy because stars do that. They do that to each other. Uh, and so what you want is not too many supernovas and not too few, because if you have too few, that's in the outskirts of the galaxy. If you have too few, then you don't get enough heavy metals to make us, because I'm made of stuff like carbon, which astronomers uh, call anything more massive than helium. They call it a metal. They just do that for convenience. So I'm made of metals, carbon, oxygen, and all that other good stuff that I need in order to be the thinking, breathing person that I am. And that all came from supernova or kilonova, if you like. And so too far away from the center of the galaxy, not enough. Supernova too close in, too many would have wreaked havoc on our souls. And is there a third thing? But that tends to be the main thing. Not too much, not too little in the way of supernova explosions. So we're lucky in that regard. And then there is, of course, our solar system itself, which has been very kind to us. And while it's bombarded us with meteors and all sorts of things and asteroids over time, and probably had a lot to do with wiping out definitely had a lot to do with wiping out the dinosaurs, but who knows how many extinctions prior to that. And so our solar system has been gentle to us. That's not to say that there aren't a trillion, and that's a number. There aren't a trillion objects in the solar system which could, if reasonably deflected, have the Earth in its sights. But as far as we know at the present time, despite that number is a trillion, none of them have us in our sights, with a 95% probability of being right, because we're still looking for that other 5%, which we can identify as not having been found yet. So there's still a possibility that we might not survive that 5%. Anyway, thanks for that. I hope that's enough of an answer. See you in the next question. So Harvey asked this question of a person he trusts on the internet, and the answer was a nice one, and I won't give that answer. But the question is, why is Carl Sagan so highly regarded when in the grand scale of things, he practically accomplished nothing? And I agree with the practically accomplished nothing from the point of view of science. He did discover that Venus is hot because of the greenhouse effect. So that is his and his alone, and his co-worker, James Pollock. But Sagan didn't do much, I agree, but he was Sagan. And who was Sagan? To me, he was a kind, gentle man with enormous insight, enormous curiosity, and enormous wisdom, and an enormous interest in promoting science. And his way of speaking was charismatic. I would just marvel at him before he was famous, because he wasn't famous quite then. But the way he talked just blew me away with how he could say something that had never been said before, and just make it understandable. And so he became a science popularizer, and as well as a good person to promote space missions. And so his word became useful. But I think it was his personality more than anything else that made him the important person that we think of to this day. To me, he was most important because He gave me my PhD. I didn't deserve it. I was not, I mean, I certainly did my thesis and it's perfectly good, but on my thesis defense, I have to say, he did say to me, Laird, I would have thought you would have done better. And then he passed me. So, but he passed me because he knew that I had been struggling with emotional problems for 2 years. And he was there to help me through my emotional problems. And he didn't do that just for me, but also for other people that I know of. So he was a great person. So I think that's why.